For most of Earth's history, immense forces deep underground have been quietly building mountains of fire. Driven by heat from the planet's interior, solid rock slowly flows, plates grind and pull apart, and molten rock finds pathways to the surface as volcanoes. Today we explore how these hidden processes create eruptions, new land, and entire volcanic chains across the globe. If you enjoy calm journeys into Earth's past, please like, subscribe and share, and tell us in the comments what would you ask about the forces that build volcanoes. Thank you for watching. Now let's begin. Earth is a differentiated planet with a clear internal structure, and this structure provides the physical context in which volcanoes form. In this view, the planet is considered as a whole system driven by internal heat and by the gradual loss of that heat through its surface. At the outermost level there is the crust, a relatively thin solid shell made of rocky material that varies in thickness between the continents and the ocean basins. Beneath the oceans, the crust is generally thinner and denser, composed mostly of basaltic rocks, while beneath the continents it is thicker on average, and often made of more varied and less dense rocks. Below the crust lies the mantle, which extends to a depth of thousands of kilometers and contains most of the volume of the planet. The mantle is solid on the timescale of a human life, but over geological time it can deform and flow slowly. At the center of Earth there is the core, which is rich in iron and nickel, and divided into a liquid outer part and a solid inner part. The outer core convects, and this motion in a metallic fluid helps generate the magnetic field that surrounds the planet. The layered arrangement of crust, mantle and core arises from early processes, when Earth is very young and still hot from accretion impacts and the separation of dense and light materials. Over billions of years the planet cools, yet it still retains a large amount of internal heat, and this heat continues to move from the deep interior toward the surface. Internal heat has several sources. One source is primordial heat, which is the remaining thermal energy from the time when the planet forms through the accumulation of smaller bodies. Another source is the decay of radioactive elements inside Earth, especially in the mantle and crust, where isotopes of uranium, thorium and potassium release heat as they transform into more stable forms. A further contribution comes from the gradual crystallization of the inner core and the slow separation of light and heavy components within the core. Together, these processes maintain temperature differences between deep and shallow regions. When a body has such temperature differences, heat is transferred by conduction, radiation and convection. In the solid parts of Earth, such as the lithosphere, which includes the crust, and the uppermost rigid mantle, heat is transferred mainly by conduction, where thermal energy passes from hotter regions to cooler regions through the vibration and movement of atoms in solid rock. Conduction is relatively slow for large distances, so in deeper regions it is not the sole process. In much of the mantle, heat transfer is dominated by convection. In convection, warmer and therefore less dense material tends to rise, while cooler and denser material tends to sink. In the mantle, this happens over millions of years, with solid rock deforming so slowly that it behaves like a very viscous fluid on long time scales. Rising regions of mantle bring heat toward the surface, while sinking regions carry cooler material downward. The combination of conductive and convective heat transfer leads to a characteristic increase of temperature with depth, known as the geothermal gradient, although the exact rate of increase differs between conductive outer layers and convecting deeper layers. This temperature profile is important because it determines whether rocks at a given depth are solid, partially molten, or fully molten. In most of the mantle, high pressure raises the melting point of rock, so that even high temperatures leave the material in a solid state. Only under particular combinations of pressure, temperature, and composition does partial melting occur and magma begin to form. The convective circulation in the mantle is not directly visible because it occurs far beneath the surface, but it can be inferred from several observations. Seismic waves from earthquakes travel at different speeds through hotter and cooler regions, and detailed studies show patterns that are consistent with upwelling and downwelling mantle. The large-scale distribution of mountain belts, ocean trenches, and broad uplifts at the surface also suggests that forces from the convecting mantle act on the outer layers. The difference in behavior between the rigid outer shell and the deeper, more slowly flowing mantle is a key condition for volcanism. The outer shell is broken into pieces that behave as mechanically strong plates over geological time. These plates are able to move because they rest on the warmer and more deformable mantle beneath. Where plates interact either by moving apart, colliding, or sliding past one another, the motion is ultimately driven by density contrasts and gravitational forces that are themselves tied to internal heat and the slow cooling of the planet. Regions of the mantle that rise beneath parts of this outer shell can bring material close enough to the surface that pressure decreases while temperatures remain high, making partial melting possible. In other settings, material that descends toward the core interacts with surrounding rock and fluids, again creating thermal and compositional contrasts that may contribute to melting. Although the detailed location, shapes and speeds of mantle circulation are still active research topics, the broad picture is well supported. Earth is a planet that slowly loses heat from its interior, and this loss is carried in large part by solid-state convection in the mantle. The rigid outer lithosphere responds to this convective system, and over time this response includes stretching, bending and breaking of the outer shell. These mechanical processes set the stage on which magma can form and move, but the first step in understanding any volcano is to recognize that it is one expression of long-term internal heat transfer within the layered interior of the planet. Earth's outer shell is not a single unbroken piece of rock, but a mosaic of plates that behave as mechanically strong units over geological time, and these plates ride on top of the underlying mantle. In a geological context, a plate is a region of the lithosphere, which is the outer rigid layer that includes the crust, and the uppermost part of the mantle, where rocks are cool and strong enough to deform only slowly or to fracture instead of flowing. The lithosphere varies in thickness from place to place, and is usually thinner beneath young ocean basins and thicker beneath old continents. Beneath the oceans, the lithosphere can be only a few tens of kilometers thick in young regions, whereas beneath stable continental interiors it can extend to depths of more than 100 kilometers. Beneath the lithosphere lies a zone of mantle that is still solid but is warmer and weaker. Over long intervals of time, this material can flow more readily. This zone is often called the asthenosphere. The contrast in mechanical behavior between the rigid lithosphere and the more deformable asthenosphere allows the plates to move as coherent blocks, while the deeper mantle circulates below them. The distinction between these layers is not based on composition alone, but on how the rocks respond to stress and temperature. Seismic studies show that there are changes in the speed of seismic waves at depths that roughly correspond to the base of the lithosphere, and these observations support the idea of a strong outer shell above a weaker region. Measurements of how Earth's gravity field varies from place to place, and how the surface flexes under loads such as ice sheets and large sediment piles, also indicate that the lithosphere behaves as a stiff mechanical layer floating on more deformable material. Over the surface of Earth, the lithosphere is divided into a limited number of major plates and several smaller plates. Some plates are large and include both oceanic and continental regions, while others are smaller and consist primarily of oceanic lithosphere. Oceanic lithosphere is generally denser and thinner than continental lithosphere, and is made mainly of basaltic crust overlying upper mantle that has cooled from higher temperatures. Continental lithosphere is thicker and less dense on average, and includes a more varied crust with many rock types. The base of each plate is defined by the depth at which the mechanical behavior of rocks changes from rigid to more ductile flow. This boundary is a zone rather than a sharp surface, but it marks the level at which mantle material can begin to accommodate deformation by flowing over geological time instead of by brittle fracture. The thickness of lithosphere increases as it cools, so old oceanic plates far from zones of formation are underlain by thicker rigid layers than young plates near ridges. The motion of plates is described in terms of rotation on a spherical planet. Each plate can be approximated as rotating around an axis that passes through the centre of Earth, and this rotation leads to relative motion between neighbouring plates along their shared boundaries. On average, plate velocities are of the order of a few centimetres per year, although rates differ among regions. These speeds are low on human timescales, but significant over millions of years during which plates can travel thousands of kilometres. Because the plates are rigid in a mechanical sense, most deformation, due to their relative motion, is concentrated at or near their edges where they meet and interact. Within the interior of a plate deformation is usually limited, and the stress field is comparatively gentle, though there are exceptions in regions where forces transmitted from boundaries or from underlying mantle flow cause intraplate deformation. The driving forces that set plates in motion are linked to density contrasts and gravity. Cold dense parts of plates that sink into the mantle, especially in subduction zones, contribute to a downward pull that helps draw the plate behind them. Elsewhere, variations in plate thickness and in the elevation of mid-ocean ridges contribute to horizontal pressure gradients along the base of the plate that can promote motion. Mantle convection beneath the plates exerts tractions on their bases and sides, and these interactions transfer momentum between the plates and the convecting mantle. Although the relative importance of each driving force is still a subject of study, the overall picture is that plate motions are responses to forces generated by density differences within Earth and by the need to transfer heat from the interior toward the surface. Observations support this framework. Global earthquake catalogues show that most earthquakes occur along narrow belts that outline the main plate boundaries, indicating that these belts are zones of concentrated stress and relative motion. Ocean floor bathymetry reveals long ridges and deep trenches that align with these zones and that mark regions where plates move apart or converge. Some boundaries are narrow and well-defined, while others are broader zones that include fault systems and regions of distributed strain. In both cases, the mechanical contrast between plates and underlying mantle controls how stress accumulates and how fractures open or close. Geodetic measurements from satellite-based systems record the present-day motions of points on the surface and show that they move in patterns consistent with the rotation of rigid plates on a sphere. The fit of continental margins and the continuity of geological structures across oceans provide further indications that plates have shifted positions relative to one another over long periods of time. These multiple lines of evidence support the concept that Earth's surface is divided into plates that move with respect to one another, and that these plates interact along their margins. From the point of view of volcanism, the presence of moving plates over a slowly convecting mantle produces zones where deformation, fracturing, and material exchange are focused. Many of these zones, particularly where plates approach separate or adjust their relative motion, later coincide with regions in which partial melting and magma movement can develop, so the distribution and nature of plates provide the large-scale surface framework within which volcanic systems arise. Knowledge of plate motions does not rely on direct watching of continents and oceans drift across the surface over millions of years, but on several converging lines of observation that record how the outer shell of Earth has changed position through time. One of the earliest clues comes from the way continental margins fit together, such as the matching outlines of some coasts on opposite sides of an ocean basin, and from the similarity of rock formations and fossil assemblages on now separated lands. Mountain belts, ancient sedimentary basins and distinctive rock types can be traced from one continent to another when they are restored to positions that would place them adjoining each other, and this geometric and geological continuity suggests that present oceans have not always existed in their current form. As more data become available, especially from the floors of the oceans, the picture of moving plates becomes more detailed. Mapping of the ocean floor reveals long mid-ocean ridges, deep trenches and fracture zones forming a connected global network of topographic features. Volcanic rocks dredged or drilled from the ocean crust are predominantly basaltic, and their distribution and age vary in a systematic way with distance from the ridges. Radiometric dating, which uses the known rates of decay of radioactive isotopes to determine the age of rocks, shows that oceanic crust is youngest at the ridges and becomes progressively older toward the continents reaching ages of only a few 100 million years, whereas many continental rocks are much older. This age pattern indicates that new oceanic crust is produced at the ridges, and that older crust is eventually removed elsewhere, fit in the concept of plates that grow at spreading centers and are consumed along other boundaries. Another key line of evidence for plate motion comes from paleomagnetism, which is the study of the record of Earth's magnetic field preserved in rocks. When certain minerals in cooling magma or in sediments align with the magnetic field, they can retain a remnant magnetization that indicates the direction of the field at the time they form. The magnetic field of Earth has a dominant component that approximates a dipole aligned roughly with the rotation axis, and over long time scales the orientation of this dipole is tied to the planet as a whole. If continents move relative to the rotation axis, the direction of the remnant magnetization in rocks of different ages on a given continent will appear to change through time. Paleomagnetic studies of rocks of varying ages on several continents reveal apparent polar wander paths, which are curves that show how the inferred position of the magnetic pole relative to that continent shifts with age. When these paths from different continents are compared, they cannot all be reconciled by a single moving pole if the continents are kept in their present positions. However, if the continents are allowed to move relative to one another, the apparent motions of the pole can be made consistent, supporting the interpretation that continents and plates travel across the surface. The ocean floor also preserves a magnetic record in the form of linear anomalies that run roughly parallel to mid-ocean ridges. As magma rises and solidifies at a ridge, magnetic minerals within it align with the current direction of the magnetic field. Over geological time, the polarity of Earth's magnetic field reverses many times, so that north and south magnetic poles exchange places. New crust formed during one polarity interval carries a remnant magnetization of that sign, and crust formed during the next interval carries the opposite sign. When marine magnetic anomalies are measured by ships or aircraft, they reveal a pattern of alternating positive and negative stripes that are approximately symmetric on either side of a ridge. When these stripes are matched with an independently dated sequence of magnetic reversals, they provide a time-calibrated record of seafloor spreading. The widths of the stripes combined with their ages give estimates of spreading rates, which are typically of the order of a few centimeters per year. These rates are consistent with other estimates of plate motion and confirm that new oceanic lithosphere is continually created at ridges and carried away. Evidence for current plate motions is now directly measured by geodetic techniques that track the positions of points on Earth's surface with high precision. Satellite-based systems such as those that use signals from networks of orbiting transmitters allow repeated measurements of the distance between fixed stations on different plates. Over intervals of years to decades, these distances change by amounts that correspond to velocities of a few millimeters to several centimeters per year, and the directions of motion agree with those inferred from geological and geophysical data. Very long baseline radio interferometry, which uses signals from distant radio sources such as quasars, provides another independent set of constraints on plate motions. Together, these techniques map how plates move at present and show that plate interiors behave approximately as rigid bodies. Earthquake distributions add further detail to the pattern of plate motion. Global seismic networks detect and locate earthquakes, and when their positions and depths are plotted, they form narrow belts along many plate boundaries. In some regions, earthquakes define inclined zones that extend from near the surface to depths of several hundred kilometers, corresponding to the paths of subducting plates. In other regions, earthquakes are concentrated at shallow depths along ridge axes or along transform faults that offset ridge segments. These patterns indicate where plates move apart, where they slide past each other, and where they converge and one plate descends into the mantle. The depth distribution of earthquakes and the focal mechanisms which describe the orientation of the fault plane and the direction of slip permit detailed reconstruction of the relative movements of plates along their boundaries. Fossil and sediment records also contain information about past plate motions. The distribution of certain fossil groups, such as specific plant species or marine organisms with narrow environmental ranges, reflects past connections between land masses and ocean basins. Sedimentary deposits that indicate particular climatic zones, such as coal-bearing strata, associated with humid tropical conditions, or glacial deposits linked to cold high-latitude environments, appear today at latitudes that differ from those implied by their depositional conditions. When continents are repositioned according to plate reconstructions, these climatic indicators align in a way that is consistent with expected global climate patterns for the time in question. These combined observations build a coherent picture of plates that move relative to each other at rates that can be quantified with trajectories that can be reconstructed back through large spans of geological time. The same framework that describes current motion helps to explain the past assembly and breakup of supercontinents and the opening and closing of ocean basins, and it allows reconstructions of how continents and ocean basins change positions through geological time. Plate boundaries are zones where neighbouring plates meet and where their relative motions are expressed through deformation faulting and in many cases magmatic activity. So these regions form the principal surface environments in which many volcanoes are found. A boundary is not always a single line, but often a belt that can be tens to hundreds of kilometers wide, within which strain is distributed among many structures. On a global scale, most plate boundaries fall into three broad kinematic categories defined by how plates move relative to each other. Plates may move apart, move toward one another, or slide laterally past each other. These categories are described as divergent, convergent, and transform boundaries. Although this classification is based on relative motion, it also correlates with characteristic patterns of deformation, seismicity, elevation, and magmatism. Divergent boundaries are regions where two plates move away from each other and new lithosphere is created. Most divergent boundaries occur along mid-ocean ridges where upwelling mantle material beneath a spreading centre contributes to the formation of new oceanic crust. The ridge axis is typically elevated compared with the surrounding seafloor because newly formed lithosphere is warm and relatively buoyant. The central part of a ridge often contains a linear valley or rift bordered by faulted blocks that indicate extension. Seismicity at ridges is generally shallow, and earthquakes are concentrated near the axis where plates separate and along transform faults that offset ridge segments. Igneous activity is persistent or frequently renewed, with magma rising to fill gaps as plates diverge, solidifying as basaltic crust that forms the upper part of the oceanic lithosphere. The thickness and physical properties of newly formed lithosphere then evolve as it moves away from the ridge and cools. Some divergent boundaries occur within continents as rifts where a landmass is stretched and thinned. In these regions, normal faults break the crust into blocks that move relative to each other, forming elongated basins and uplifts. The crust may be intruded by dikes and sills of magma, and volcanic centers may develop where magma reaches the surface. Sedimentary basins within rifts can accumulate thick successions of sediments eroded from surrounding highlands, and these basins may later record the transition from continental to marine conditions if rifting progresses. Gravity and seismic data from rift zones reveal that the crust and upper mantle are modified by both mechanical stretching and magmatic intrusion. If rifting continues for sufficient time, a continental rift can evolve into a new ocean basin, with a mid-ocean ridge linking continental extension and oceanic spreading as stages along a continuous process of divergence. Convergent boundaries are regions where plates move toward each other. In many cases, an oceanic plate descends beneath another plate, forming a subduction zone. The interface between the descending plate and the overriding plate is marked by intense deformation and seismic activity, with earthquakes occurring along a dipping zone that traces the path of the subducting slab to depths of several hundred kilometers. Above the subduction zone, the overriding plate may host a chain of volcanoes that roughly parallels the trench. These volcanic arcs can be located on continental crust or on oceanic crust, forming island arcs. The spacing between the trench and the volcanic front is controlled by the geometry of the subducting slab and the depth range over which melting in the mantle wedge above the slab is most efficient. The presence of water and other components carried down by the subducting plate influences the conditions under which melting occurs in this mantle wedge, and this link between subduction mantle melting and arc volcanism is a central feature of many volcanic systems on Earth. At some convergent boundaries, the collision involves two continental plates. In such cases, neither plate readily sinks because continental lithosphere is relatively buoyant. The result is thickening of the crust uplift and mountain building, with a complex pattern of faults and folds. Magmatic activity may still occur in these collisional settings, but it often differs in character and distribution, from arc volcanism above classic oceanic subduction zones, and may be focused in regions where the thickened crust becomes hot enough for partial melting. Transform boundaries are zones where plates slide horizontally past each other. Motion along transform faults accommodates differences in spreading rates or directions between segments of divergent boundaries, or adjustments between convergent and divergent segments in complex plate boundary systems. Along oceanic transforms, narrow belts of shallow earthquakes mark the active faults, and volcanic activity is typically limited to the ridge segments that they connect. On continents, transform boundaries can be expressed as broad zones of strike-slip, faulting with distributed deformation. Fault traces may bend step over or branch, creating local regions where the crust experiences extension or compression superimposed on the dominant lateral motion. In areas where extension develops, crustal thinning can favor limited magmatic intrusion or small volcanic centers, whereas compressional jogs may localize uplift and crustal thickening without much volcanism. Overall volcanism associated directly with transform motion is generally less common and less volumetrically significant than at divergent and convergent boundaries. But local magmatic activity can occur where geometrical complexities or changes in stress create favorable conditions along the boundary. The global pattern of active volcanoes reflects these boundary types. Many of the most persistent and numerous volcanoes lie along convergent margins, especially around the margins of the Pacific Ocean, where several plates converge and broad subduction systems form an extensive belt of volcanic arcs and deep trenches. Long but narrower belts of volcanic activity follow mid-ocean ridges, where eruptions occur mostly underwater and contribute continuously to the formation of new oceanic crust. Continental rifts host fields of volcanoes and volcanic plateaus that may be widely spaced, but that mark regions where the lithosphere is thinning and extension is active. Hotspot-related volcanoes which can occur away from plate boundaries add further complexity, But even in those cases, the motion of plates over relatively fixed sources produces linear chains of volcanic edifices that still record plate motion. Taken together, plate boundaries are zones where mechanical interaction, fracture and displacement are concentrated, and where pathways for magma generation and ascent are favoured compared with plate interiors, so the large-scale distribution of volcanoes across Earth's surface is closely associated with the geometry and behaviour of these boundaries. Subduction zones are convergent plate boundaries where one plate bends and descends beneath another into the mantle, and they are among the most important settings for the formation of volcano chains known as volcanic arcs. In most cases, the descending plate is an oceanic plate which is denser than the plate that remains above. At the surface, the boundary between the two plates is marked by an oceanic trench, if at least one plate is oceanic. These trenches are elongated depressions that parallel the plate boundary and reach some of the greatest water depths observed in the oceans. Landward of the trench on the overriding plate, there is often a region called the forearc, which may include ridges and basins, and in many systems an accretionary prism built from sediments scraped off the top of the downgoing plate and deformed against the front of the overriding plate. The geometry of a subduction zone is described by the dip of the slab, which is the angle between the descending plate and the horizontal. This angle can vary widely between different systems, from shallow dips that extend over long horizontal distances to steep slabs that plunge into the deeper mantle over relatively short horizontal spans. Earthquake distributions define inclined zones that trace the path of the subducting plate to depth of several hundred kilometers. These zones, called Wadati-Benioff zones, contain both shallow and intermediate depth earthquakes, and in some cases deeper events. The pattern of seismicity provides information on the mechanical coupling between plates, the stresses acting in the slab and the depth range over which brittle failure is still possible. Above the subducting plate and landward of the trench, a chain of volcanoes often develops on the overriding plate. This chain, termed a volcanic arc, may form on continental crust, producing a continental volcanic arc, or on oceanic crust, producing an island arc. The position of the arc relative to the trench is related to slab geometry and to the depth at which mantle above the slab undergoes significant melting. Typical distances between the trench and the volcanic front are on the order of a few hundred kilometers, but the exact spacing is sensitive to the dip angle of the slab and to the structure of the overriding plate. The volcanoes in an arc are not continuous along strike, but are grouped into segments with variable spacing and size. Segmentation is influenced by changes in convergence rate and direction variations in slab age and buoyancy, inherited structures in the overriding plate, and the distribution of faults and fractures that can act as pathways for magma ascent. The age and thermal state of the subducting plate influence the dynamics of a subduction zone. Older oceanic lithosphere is colder and denser than younger lithosphere, and tends to sink more readily, contributing to a stronger slab pull force. As oceanic lithosphere ages, its crust and underlying mantle portion cool, and undergo mineral transformations, including the conversion of basaltic crustal rocks into denser assemblages such as eclogite at high pressures, which further increase the negative buoyancy of the slab. In contrast, young and hot oceanic lithosphere is less dense relative to the surrounding mantle and may resist subduction or descend at shallower angles. In some settings, buoyant features on the subducting plate, such as oceanic plateaus or thick sediment piles, modify the local geometry of the slab and can interrupt or reconfigure volcanic activity above. The overriding plate also responds to subduction through deformation, uplift, and subsidence. In continental settings, convergence leads to crustal shortening folding and thrust faulting, building mountain belts that parallel the trench and arc. Crustal thickening raises the surface and can change the pressure and temperature conditions in the lower crust. In some arcs, crustal thickness reaches several tens of kilometers, and this thickened crust can influence the storage and evolution of magmas beneath volcanoes. In oceanic island arcs, the overriding plate is thinner and composed mainly of oceanic lithosphere, so deformation may be more focused near the trench and arc, and the resulting topography is often expressed as chains of islands separated by deep basins. The forearc region typically experiences low heat flow compared with the volcanic arc and back arc regions, reflecting the cooling influence of the descending slab and the absence of large magma bodies at shallow depth. Fluids released from the subducting plate move into the overlying mantle wedge and crust, but the detailed paths and rates depend on permeability structure and pressure conditions. In contrast, the arc region is characterized by elevated heat flow, active or recent volcanism, and a crust that is often intruded by plutons and dikes that represent frozen magma bodies at different depths. These intrusions contribute to long-term growth and modification of the crust beneath volcanic arcs. The chemical and physical properties of volcanic rocks erupted in arcs differ on average from those at mid-ocean ridges. Arc volcanoes commonly erupt magmas with intermediate to silicic compositions such as andesites and dacites along with basalts. These magmas often contain significant amounts of dissolved volatile components, including water and carbon dioxide, and their interaction with the surrounding crust can further modify their compositions. The high volatile content and higher viscosity of many arc magmas favour explosive eruptive behaviour, generating pyroclastic deposits and widespread ash layers, in addition to lava flows. The proportions of lava flows, pyroclastic material and intrusive bodies vary among arcs and among individual volcanoes within a given arc. Many arc volcanoes are composite edifices built from alternating layers of lava and pyroclastic material, and their slopes and internal structures reflect the balance between effusive and explosive activity over time. Back arc regions located on the far side of the arc relative to the trench can display varied tectonic and magmatic behaviour. In some systems, extension occurs in the back arc forming basins and even small spreading centres where new crust is created, and volcanism can be distributed across the arc and back arc. In other systems, the back arc is relatively stable or experiences compression. The state of stress in the back arc is influenced by factors such as slab rollback, where the trench and slab migrate toward the oceanic plate, and by the mechanical properties of the overriding plate. These differences in back arc dynamics feed back on the pattern of volcanism by altering crustal thickness, faulting, and the distribution of magma pathways. Observational data from many convergent margins show clear spatial associations among trenches, volcanic arcs and back arc provinces, which together define the characteristic architecture of subduction-related systems at the scale of whole plates. Within this architecture, volcanic arcs mark the zones where magma generated, in association with subduction, reaches the surface and builds long-lived chains of volcanoes with distinctive structures and eruptive styles. Mid-ocean ridges are linear to curved belts on the ocean floor where plates move apart and new oceanic lithosphere forms, and they represent one of the most extensive volcanic systems on Earth. These ridges form a connected global network that winds through all major ocean basins with individual segments, separated by transform faults and smaller offsets. Bathymetric surveys show that ridge axes stand above the surrounding sea floor as broad topographic highs. This elevation reflects the relatively high temperature and low density of the young lithosphere near the spreading centre, compared with older, cooler lithosphere farther away. The ridge crest often contains a central rift valley or axial depression, which is bounded by normal faults that accommodate extension as the plates diverge. The width, depth, and morphology of this axial region vary along the ridge and among different ridge systems, and these variations are linked to spreading rate magma supply and the thermal structure of the lithosphere. Seismicity at mid-ocean ridges is concentrated at shallow depths. usually within a few kilometers of the seafloor, and reflects small magnitude earthquakes that occur as plates pull apart and as magmatic intrusions open cracks in the crust. These earthquakes define narrow zones along the ridge axis and along transform faults that offset the ridge. Focal mechanism solutions indicate normal faulting within the rift valley, and strike-slip motion along transforms consistent with extension, oriented perpendicular to the ridge and horizontal shear along the offsets. The pattern of seismicity confirms that ridge segments are boundaries where plates separate and where brittle deformation in the upper lithosphere adjusts to the continuous creation of new crust. The crust formed at mid-ocean ridges is predominantly basaltic and has a characteristic layered structure. Geophysical studies, including seismic refraction experiments, reveal a sequence of layers with differing seismic velocities that are interpreted as from top to bottom. Sediment cover extrusive volcanic rocks, a complex of sheeted dikes and gabbroic rocks that crystallize from magma at greater depth. This crustal package overlies upper mantle peridotite that has been cooled from higher temperatures. Sampling by dredging, drilling and submersible dives confirms the presence of pillow lavas and sheet flows at the surface, which are forms of basalt that solidify when magma erupts and cools rapidly in contact with seawater. Beneath these lavas, numerous vertical to subvertical dikes record repeated injection of magma that feeds eruptions at the seafloor. At still greater depths, coarser-grained rocks preserve the crystallization of magma bodies within the crust. The thickness of typical oceanic crust generated at ridges is on the order of several kilometers and remains relatively uniform across many segments, which suggests a broadly similar magmatic production rate averaged over time, even though short-term activity may fluctuate. The rate at which plates diverge at a ridge, known as the spreading rate, influences the form and behavior of the ridge system. Slow-spreading ridges have total opening rates of only a few centimeters per year or less, leading to relatively deep and rugged axial valleys, discontinuous magma chambers, and a more pronounced role for tectonic extension in shaping the seafloor. Fast-spreading ridges, in contrast, may have smoother axial highs, without a deep rift valley, more continuous magma lenses beneath the axis and volcanic construction that plays a larger part in forming the ridge topography. Intermediate spreading rates produce morphologies that share features of both end members. Despite these differences, all ridge types are sites where basaltic magma is brought to the surface, or near surface, where it solidifies to form new crust as plates move apart. Heat flow measurements across ridge systems show high values near the axis that decrease with distance, consistent with newly formed lithosphere that cools and thickens as it is carried away. As this lithosphere cools, the seafloor subsides, giving rise to the systematic increase in water depth with age that characterizes the major ocean basins. This cooling also increases the mechanical thickness and strength of the lithosphere, affecting how it later behaves in other tectonic settings, including future subduction zones. Hydrothermal circulation is an integral part of many ridge environments. Seawater penetrates into the permeable oceanic crust through fractures, and porous layers is heated by contact with hot rocks and shallow magma bodies, and then rises back to the seafloor where it discharges as hot fluids at hydrothermal vents. These fluids can reach temperatures of several hundred degrees Celsius and often carry dissolved metals and other components leached from the crust, which precipitate as mineral deposits when the fluids mix with cold seawater. The circulation of fluids alters the mineralogy and physical properties of the crust, changing its density, strength, and permeability. It also plays a role in the transfer of heat from the interior to the ocean and can modify the chemistry of seawater over long timescales. The existence of these systems indicates that the interface between magma rock and seawater at mid-ocean ridges is active, even though the underlying process of plate separation is relatively steady on geological timescales. The spatial arrangement of ridge segments and transform faults reflects both the geometry of plate motions and the rheology of the lithosphere. Ridge axes are commonly offset by transforms that are oriented roughly perpendicular to the spreading direction. These transforms accommodate differences in motion between adjacent ridge segments and are themselves plate boundaries with their own seismic characteristics. Non-transform offsets, such as overlapping spreading centers and small discontinuities, reveal additional complexity. Variations in magma supply along the ridge can lead to segment centers that are magmatically robust and segment ends where magmatic activity is less intense and where tectonic extension may dominate. Over time, this segmentation influences the distribution of volcanic edifices, fissure eruptions and lava flow fields on the seafloor. Although most mid-ocean ridge volcanism occurs beneath the ocean and is not directly observed in real-time monitoring with seafloor instruments, water column surveys and remote sensing has documented episodes of dike intrusion and eruption. These events may involve the propagation of magma-filled fractures over distances of several kilometers along the axis, the opening of new fissures, and the emplacement of fresh lava flows that can be mapped soon after eruption. Geophysical, geological, and geochemical observations identify mid-ocean ridges as continuous yet segmented volcanic systems in which the production of new oceanic crust keeps pace over long intervals with the separation of plates. Continental rifts are regions where a continent is stretched and thinned over geological time, and they represent another important environment in which volcanic activity develops as part of plate divergence. In a rift, the lithosphere experiences horizontal extension, and this extension is accommodated by brittle faulting in the upper crust and by ductile flow or distributed deformation at greater depths. Normal faults, which are faults on which the hanging wall moves downward relative to the footwall, break the crust into blocks that can tilt and subside, forming elongated depressions known as grabens and intervening uplifted blocks known as horsts. On the surface, these structures appear as long valleys bordered by steep escarpments, often arranged in en-echelon patterns along the rift. The cumulative effect of many such faults is to reduce the thickness of the crust across the rift zone. Gravity measurements commonly reveal lower gravity anomalies over rift basins due to the presence of thick accumulations of relatively low-density sediments and higher anomalies over uplifted flanks where denser rocks may be closer to the surface. Seismic reflection and refraction studies show that crustal thickness decreases beneath mature rifts compared with adjacent regions, and that the base of the crust may be irregular, where intrusions and underplated material have modified the crust mantle boundary. Heat flow is typically elevated in rift zones relative to stable continental interiors, consistent with thinning of the insulating lithosphere and with the presence of magmatic bodies at depth. The development of a continental rift is often described in terms of stages. In an initial stage, regional stress fields associated with plate scale forces or with mantle upwelling begin to extend the lithosphere. Small faults form and may link into larger fault systems. As extension continues, fault activity localizes along major boundary faults that define one or more main rift valleys. The crust is progressively thinned and subsidence of the rift floor creates space that can be filled by sediments derived from the surrounding highlands and by volcanic rocks. In some systems, uplift of the rift shoulders occurs as the crust flexes in response to faulting and as lower density material is in place beneath the rift. At more advanced stages, if extension persists, the lithosphere can become sufficiently thinned that hot asthenospheric mantle rises to shallower depths beneath the rift axis. This upwelling enhances decompression, melting producing basaltic magmas that can intrude the crust and in some cases erupt at the surface. Magmatic activity in rifts has several manifestations. One common feature is the presence of dike swarms, which are tabular intrusions of magma that cut across existing rock structures and trend roughly parallel to the axis of extension. These dikes represent conduits through which magma moves upward or laterally. Their orientations record the principal directions of stress during intrusion. Sills, which are sheet-like intrusions that are concordant with layering in the host rocks, may also form especially in sedimentary sequences within the rift basin. At greater depths near the base of the crust, magma ponds and cools to form intrusive complexes and underplated bodies that add mafic material to the lower crust. This addition changes the composition density and seismic properties of the crust and can influence how it deforms later. At the surface, rift-related magmatism can produce a variety of volcanic landforms. Basaltic lava flows may spread across the rift floor, filling depressions and burying older sediments. Repeated eruptions can build volcanic plateaus and gently sloping shield volcanoes. In some rifts, numerous small monogenetic cones formed by one or a few eruptions each are scattered across the landscape supplied by magma, rising along fractures and faults. Larger central volcanoes may form where magma supply is sustained and focused, often near intersections of major fault systems, or where crustal structure favours the formation of long-lived magma reservoirs. Volcanic activity may be distributed across the rift, or concentrated along particular segments, depending on variations in extension rate, lithospheric thickness, and mantle temperature. The composition of rift magmas is most often basaltic, reflecting partial melting of the upper mantle, but a spectrum of compositions can be produced where magmas interact with and partially melt the continental crust or undergo fractional crystallization in crustal magma chambers. More evolved magmas with higher silica content can give rise to more viscous lavas and explosive eruptions that create pyroclastic deposits and caldera structures. The balance between basaltic flood lavas, central volcanoes and explosive silicic centers varies among rift systems and evolves through time as the thermal and mechanical state of the lithosphere changes. Sedimentation within rift basins occurs concurrently with tectonic and magmatic processes. Rivers and alluvial fans transport material from rift shoulders into the subsiding basin where it accumulates in thick sequences interbedded with volcanic products. Lakes may form enclosed depressions, especially during wetter climatic periods, and their sediments can preserve fine-grained records of environmental conditions and volcanic ash layers. The interaction of lacustrine or fluvial systems with volcanic activity can produce distinctive deposits such as hyaloclastites from lava entering water or reworked ash in deltic environments. Over time, the combined thickness of sediments and volcanic rocks may reach several kilometers, contributing to further subsidence through loading. The thermal regime in rifts promotes hydrothermal circulation, with fluids moving through faults and fractures and exchanging heat and chemical components with surrounding rocks. This circulation can lead to the formation of mineral deposits and can influence the mechanical properties of fault zones by altering rock strength and pore pressure. Geophysical imaging of rifts using seismic tomography and magnetotelluric methods often reveals zones of reduced seismic velocity or increased electrical conductivity at depth beneath rift axes interpreted as regions of partial melt or regions containing hot fluids. These observations support the idea that significant volumes of molten or partially molten material can be present in the lower crust or upper mantle beneath active rifts even when surface volcanism is intermittent. Continental rifts do not all evolve in the same way. Some remain in a prolonged state of extension, without progressing to full continental breakup, becoming wide zones of thinned crust, with complex fault networks and limited magmatic activity. Others transition into new ocean basins when extension leads to rupture of the continental lithosphere and the onset of steady seafloor spreading. In such cases, the volcanic character of the system shifts from mainly continental rift volcanism to oceanic ridge volcanism as a continuous belt of new oceanic crust begins to form. Even after seafloor spreading is established, remnants of the earlier rift architecture may persist along the margins as inherited structures that influence later tectonic and magmatic events. Young volcanic fields associated with continental rifts provide visible records of the interplay between extension mantle melting and magma ascent. Their spatial relation to active faults and to zones of crustal thinning illustrates how tectonic structures can focus pathways for magma. Their rock types and eruptive histories preserve information about melting conditions in the mantle and about processes of magma evolution in the crust. By examining these fields together with geophysical and structural data, it is possible to reconstruct the sequence of events by which continental lithosphere stretches, thins, and becomes a site of significant volcanism during the broader cycle of plate divergence. Hotspots and intraplate volcanic regions are areas where volcanic activity occurs away from the main plate boundary belts, and they provide additional context for understanding how magma generation and volcanic construction can take place within plates rather than only along their edges. A hotspot is commonly defined as a region of long-lived, relatively focused magmatic activity that remains approximately stationary with respect to the deep interior while plates move over it. As a result, chains of volcanoes and seamounts can form on the moving plate, with the age of volcanic edifices increasing in a systematic way along the chain away from the currently active centre. Oceanic examples of this pattern include linear seamount and island chains, where the youngest volcano lies near a region of elevated heat flow and crustal thinning, and progressively older, eroded and subsided volcanoes extend along the projected direction of plate motion. The volcanic rocks along such chains often share certain chemical features that distinguish them from typical mid-ocean ridge basalts, indicating that the magmas are derived from sources in the mantle that have different histories and compositions. On continental lithosphere, intraplate volcanic fields attributed to hotspot-like processes can appear as clusters or chains of volcanoes and volcanic plateaus within plate interiors, sometimes associated with regions of regional uplift or crustal doming. The magmatism in these settings may be more diverse in composition than in many oceanic hotspots, because continental crust can influence magma evolution through partial melting assimilation and prolonged storage. The concept of mantle plumes is frequently invoked to explain hotspots. A mantle plume is proposed as a column of anomalously hot mantle material that rises from depth toward the base of the lithosphere. As the plume head or plume tail approaches shallower levels, the pressure decreases while the temperature remains relatively high compared with the surrounding mantle, allowing partial melting to occur beneath the lithosphere. The resulting magmas then intrude and erupt through the overlying plate. In some models, an initial large plume head can generate extensive flood basalt provinces when it first reaches shallow depths, followed by a narrower plume tail that feeds a more localized hotspot track over a longer time. Observational support for plume-like structures includes seismic tomography images that show regions of reduced seismic wave speeds beneath some hotspots extending through significant portions of the mantle consistent with higher temperatures or partial melt. Geoid anomalies and dynamic topography, reflected in regional patterns of surface uplift or subsidence, also suggest that buoyant upwellings or downwellings occur beneath certain regions. However, the detailed geometry, depth of origin and temperature contrasts of many inferred plumes are subjects of ongoing research, and in some intraplate volcanic areas, alternative explanations emphasize shallower mantle processes or lithospheric structures. In oceanic intraplate hotspots, volcanic construction often produces large shield volcanoes, built mainly from low viscosity basaltic lava flows that spread over wide areas and pile up to great thickness. The volcanic edifices can rise several kilometers above the surrounding seafloor, and their summits may emerge above sea level to form islands. Over time, as the plate continues to move, an individual volcano is carried away from the primary magma supply and becomes inactive. Thermal subsidence of the underlying lithosphere and loading by the volcanic edifice cause the seafloor beneath the volcano to sink. Wave erosion and subsidence transform exposed islands into seamounts, and in some cases into atolls and guyos, where carbonate platforms form on subsiding volcanic foundations. Drilling and geophysical data from such structures show sequences of volcanic rocks overlain by sediments and reef limestones that record this transition from active volcanic island to submerged seamount. The volumes of magma produced at major hotspots can be substantial, and the timescales involved may extend over tens of millions of years. Continental intraplate volcanic systems display wider variability in structures and compositions. Some are marked by large volcanic plateaus built from repeated basaltic flood eruptions that cover broad regions with thick lava sequences. Others consist of fields of small monogenetic cones maars and short lava flows distributed over wide areas. In some cases, long-lived central volcanoes develop accompanied by caldera-forming eruptions if evolved gas-rich magmas accumulate in the crust. The relationship between these volcanic expressions and underlying mantle processes is inferred from geophysical imaging and from geochemical studies of erupted rocks. Isotopic ratios and trace element patterns in intraplate basalts often point to mantle sources that differ from those feeding mid-ocean ridges, suggesting that portions of the mantle beneath hotspots retain heterogeneities related to earlier recycling of crustal material or to long-term isolation of certain mantle domains. The lithosphere itself can influence how hotspot-related magmas are focused and expressed. Regions of thinner lithosphere or pre-existing zones of weakness such as ancient rift systems or large fault zones may provide easier pathways for magma ascent. In thick, strong lithosphere, melts may stall or spread laterally at particular depths, leading to broad distributed volcanism or to intrusion-dominated regimes without large surface edifices. Local stress fields, whether extensional, compressional or strike-slip, affect the orientation of fractures and dikes, which controls how magma pathways are organized in plan view. In some hotspots situated near plate boundaries, interactions between plume-related upwelling and boundary processes can produce complex patterns of volcanism that share features of both intraplate and boundary-oriented activity. Distinguishing hotspots from other intraplate volcanism requires combining several lines of evidence. Age progressions along volcanic chains, alignment with known plate motion vectors, and approximate fixity of the magma source relative to deep mantle reference frames support a hotspot interpretation in some cases. Elsewhere, intraplate volcanoes are more scattered in age and space, and their occurrence appears closely tied to regional extension or lithospheric flexure rather than to a stationary mantle source. In these settings, decompression melting beneath zones of uplift or extension in the plate interior may be sufficient to account for observed volcanism without invoking narrow, deep-rooted plumes. Seismic and gravity data can help discriminate between these possibilities by imaging density and velocity structures at depth, while geochemical signatures constrain the nature of mantle sources and the extent of crustal interaction. The presence of hotspots and intraplate volcanic regions shows that volcanic activity is not confined to the main plate boundaries, and that magma generation can occur wherever mantle conditions and lithospheric structure combine to allow partial melting and ascent within a plate. The spatial and temporal patterns of this activity, when integrated with plate kinematics and mantle imaging, are used to infer the distribution of upwellings and heterogeneities in the mantle, and to refine models of how plates in the underlying mantle interact across different depth ranges. Decompression melting is a process in which hot mantle rock begins to melt because the pressure acting on it decreases as it rises, while its temperature remains high, and it is a central mechanism for magma generation beneath mid-ocean ridges and many continental rifts. The mantle at depths corresponding to the upper asthenosphere is composed mainly of peridotite, a rock rich in olivine and pyroxenes, which is solid under most conditions in Earth's interior. Whether this rock is solid or partially molten depends on its temperature, its pressure, and its composition, including the presence of minor volatile components. Experimental studies on peridotite and on compositions that approximate the upper mantle show that the temperature at which melting begins, called the solidus, increases with pressure. At a given temperature, increasing depth and pressure can keep the rock solid, while reducing pressure at roughly constant temperature can bring the rock into a field where partial melting occurs. The geothermal gradient in the convecting mantle is often close to adiabatic, meaning that the temperature of a rising parcel of mantle changes mainly because of expansion and compression as it moves without large amounts of heat exchange with its surroundings. In such a case, a rising parcel carries its heat upward almost conservatively. If the path of this parcel in pressure-temperature space crosses the solidus, melting begins. At mid-ocean, ridges plate separation at the surface creates a need for material to fill the space between diverging plates. The asthenospheric mantle beneath the ridge moves upward to supply this material. This is sometimes called passive upwelling because the main driver is the plate motion that creates a gap at the top rather than a buoyancy force acting on the upwelling mantle itself. As mantle material ascends toward the ridge axis, its pressure decreases in step with the reduction in overlying rock. If the starting temperature of this mantle is sufficiently high, its upward adiabatic path intersects the solidus at some depth, and partial melting starts. The depth at which melting begins depends on mantle potential temperature composition and the presence of volatile components. Beneath many ridges, estimates based on petrological and geophysical data indicate that melting initiates at depths of on the order of several tens of kilometers, and that the zone of partial melting extends upward over a significant vertical interval, until either the mantle becomes too cool or melt is largely removed. The process of melting does not convert all the solid mantle into liquid. Instead, small fractions of melt form along grain boundaries and in microstructural sites within the solid matrix. As melting proceeds, the composition of the remaining solid and of the melt evolve because melt tends to be enriched in certain components relative to the source. The degree of melting expressed as the proportion of melt generated relative to the original solid can vary from a few percent to several tens of percent, depending on depth and local conditions. Higher degrees of melting typically occur at shallower depths within the melting column, where ongoing upwelling and melt extraction draw the system further away from its original state. Melt generated in this way is less dense than the surrounding solid and tends to migrate upward. The mechanism of melt extraction involves porous flow through the partially molten matrix, focused flow through higher permeability channels, and eventual localization into dikes and larger conduits. The details of this extraction process are complex and depend on permeability, grain size, melt viscosity, and stress. Numerical models and theoretical treatment suggest that even small initial variations in melt fraction or composition can lead to the development of channels that concentrate melt flow, which in turn can react chemically with the surrounding mantle, modifying both the residue and the melt. Seismic and magnetotelluric studies of ridge regions provide evidence for the presence of partial melt beneath spreading centers. Zones of reduced seismic wave speeds and increased electrical conductivity beneath the axis and flanking regions are consistent with mantle that contains interconnected melt at certain depths. The geometry of these anomalies suggests that melting is not restricted to a narrow vertical conduit directly beneath the ridge, but may occur over a wider region that narrows as depth decreases, forming a triangular or trapezoidal melting domain in cross-section. Within this region, melt rises and is focused toward the axis where it eventually collects in crustal magma chambers, or intrudes directly into the lower crust and uppermost mantle. At fast-spreading ridges, geophysical imaging often identifies relatively continuous magma lenses beneath the axis, indicating a steady supply of melt that can crystallize to form new crust. At slow-spreading ridges, magma bodies may be more discontinuous, and the mantle may reach shallower levels without complete extraction of melt, leading to a more heterogeneous crust-mantle transition. The composition of mid-ocean ridge basalts reflects the integrated effect of decompression melting and melt extraction. These basalts are typically low in potassium and other incompatible elements compared with many other volcanic rocks, which indicates that they represent aggregated melts from moderate degrees of melting of a depleted mantle source. Variations in basalt chemistry along ridges, including changes in sodium content and in trace element ratios, provide constraints on the thickness of the melting column, the degree of melting and the fertility of the mantle. Regions where basalts are more enriched in incompatible elements are often interpreted as areas where the degree of melting is lower, or where the source mantle contains higher proportions of components that melt more readily. These inferences align with geophysical observations that show along-axis variations in crustal thickness and in mantle structure. In continental rifts, decompression melting operates under conditions influenced by thicker and compositionally more complex lithosphere. Extension and thinning of the lithosphere reduce the pressure at the top of the asthenosphere and allow warmer mantle material to rise to shallower depths beneath the rift axis. If the mantle potential temperature is sufficiently high, the ascending mantle crosses its solidus and partial melting occurs. The presence of volatiles and of compositional heterogeneities inherited from earlier tectonic events can modify the onset of melting, but the primary driver remains the decrease in pressure due to upwelling under an extending plate. The melt fractions and depth of melting in rifts can vary widely, depending on extension rate, initial lithospheric thickness, and any contribution from deeper upwellings. Geophysical imaging of active rifts often reveals low velocity and high conductivity zones beneath the central parts of the rift, interpreted as regions where partially molten mantle or melt-rich lower crust is present. The interaction of rising melts with continental crust introduces additional processes such as assimilation of crustal material and storage in crustal reservoirs. But the initial generation of magma in many rifts still involves decompression, melting of mantle that is brought to shallower levels by extension-driven upwelling. The efficiency with which melt is focused from the broader melting region towards specific volcanic centers affects the surface expression of decompression melting. In some ridge and rift systems, magma supply is sufficient to build prominent volcanic edifices and large lava fields, while in others, much of the melt may crystallize at depth or be intruded laterally as dikes and sills without extensive surface eruptions. Differences in focusing efficiency are influenced by the geometry of the lithosphere-asthenosphere boundary, by pressure gradients associated with dynamic topography, and by local and regional stress fields that control fracture orientation. Observations of temporal variations in ridge and rift volcanism, including episodic dike intrusion events and periods of reduced eruptive activity, indicate that decompression, melting, and melt extraction are continuous on geological timescales, but can show significant short and medium-term fluctuations in space and time. Experimental petrology, geochemical analysis of erupted basalts, and geophysical imaging together support a framework in which decompression, melting beneath spreading ridges and continental rifts, generates significant volumes of basaltic magma whenever mantle material at appropriate temperature is allowed to rise, and in which the geometry of upwelling and the physical properties of the mantle and lithosphere shape the size distribution and timing of melt production in these divergent tectonic environments. Flux melting is a mechanism of magma generation in which the addition of volatile rich fluids to solid mantle lowers its melting temperature so that partial melting can occur under conditions where the mantle would otherwise remain entirely solid, and this process is characteristic of the mantle wedge above subducting slabs in convergent margin settings. The starting materials involved in flux melting at subduction zones include the subducting oceanic plate overlying sediments and the mantle wedge, which is the region of upper mantle situated between the down-going slab and the overriding plate. Oceanic lithosphere acquires significant amounts of water and other volatiles before it ever begins to descend. Near mid-ocean ridges, hydrothermal circulation of seawater through newly formed oceanic crust alters basalt and gabbro by forming hydrous minerals such as amphiboly chlorite and other hydrated phases. Serpentinization of the uppermost mantle portion of the lithosphere can incorporate water into minerals such as serpentine. Pelagic sediments and sediments derived from continental sources may also contain clay minerals, organic material and carbonate that host water and carbon dioxide. As this composite package of altered basaltic crust, serpentinized upper mantle, and sediments enters a subduction zone, it is carried to progressively greater depths and experiences increasing pressure and temperature along its path. With increasing depth, hydrous minerals within the slab become unstable and undergo dehydration reactions. In these reactions, one set of minerals breaks down and releases water, while new denser mineral assemblages form that contain less structurally bound water. The sequence of dehydration depends on the particular minerals present and on the pressure-temperature trajectory of the slab. At relatively shallow depths, clay minerals and some low-temperature hydrous phases in sediments decompose, releasing fluids into the surrounding rocks. At greater depths in the basaltic oceanic crust, amphibolae and other hydrous minerals break down. In the underlying serpentinized mantle portion of the slab, serpentine and brucite can persist to considerable depths, but eventually transform into denser, nominally anhydrous phases, again releasing water. Some slab models include high-pressure hydrous minerals such as lawsonite and certain micas that stabilize at intermediate depths and then decompose at deeper levels, producing further pulses of fluid. The net effect is that as the slab descends, it expels a series of aqueous fluids and volatile-rich phases into the overlying mantle wedge and possibly into the lower crust of the overriding plate. These fluids and supercritical solutions are less dense than the surrounding rocks, and tend to migrate upward and away from the slab along grain boundaries, fractures and permeable pathways. The distribution of fluid pathways is controlled by the permeability structure of the mantle wedge, which is influenced by temperature, mineralogy and stress. Where permeability is high, fluids may percolate through diffuse networks. Where it is low overpressure, can develop and drive fracture formation or reactivation. As fluids rise into hotter regions of the wedge, they encounter peridotite that is close to but still below its dry solidus. The introduction of water and other volatiles into this peridotite shifts its melting relations. Experimental petrology shows that even small amounts of water can significantly reduce the solidus temperature of peridotite at a given pressure. Carbon dioxide and other components have similar but distinct effects, modifying both the onset of melting and the compositions of the resulting melts. When hydrous fluids infiltrate wedge peridotite at depths, where temperatures are already relatively high, because of the thermal structure of the subduction zone, the new composite system crosses into a regime where partial melting is thermodynamically allowed. Melting proceeds in a zone that is often located above the slab at depths of roughly several tens to over 100 kilometers, depending on slab age convergence rate and wedge temperature. The region in which flux melting is most intense is typically associated with the corner of the mantle wedge, where flow induced by slab motion brings hot material into contact with a fluid influx. The mantle wedge is not static. Viscous coupling between the downgoing slab and the overlying mantle induces a pattern of flow in which mantle is drawn down with the slab near the interface, then turns and rises toward the base of the overriding plate farther above the slab. This corner flow continually brings relatively warm mantle from deeper parts of the wedge into the region where slab-derived fluids are released. The combined effect of advective heat transport by wedge flow and fluid addition from the slab creates a zone where temperatures and volatile contents together favour partial melting of peridotite. The resulting melts are hydrous and generally more oxidized than those generated beneath mid-ocean ridges by decompression alone. They start their existence at depths and pressures consistent with their origin in this hydrated wedge environment. These primary melts tend to be basaltic to basaltic andesitic in composition, but their exact major element and trace element signatures depend on the degree of melting, the composition of the mantle source, and the character of the fluids. As melting proceeds, the residue in the wedge becomes depleted in components that concentrate into melts, such as certain alkali and alkaline earth elements, and incompatible trace elements, while the melt itself becomes enriched in these components relative to the bulk source. Geochemical studies of arc lavas and mafic inclusions in more evolved arc rocks show characteristic enrichments in elements such as large ion lithophile elements, and in certain isotope ratios that point to contributions from altered oceanic crust and sediments. Elevated water contents inferred from mineral assemblages and melt inclusion analyses support the interpretation that these magmas originate from flux-melted volatile rich sources rather than from purely dry decompression melting. Flux melting is not spatially uniform across the wedge. The geometry of the slab controls where dehydration reactions occur, and therefore where the main flux of fluids enters the wedge. Steeper slabs bring hydrated portions into hotter regions more quickly, potentially shifting the melting region closer to the trench, whereas shallow slabs may position the main melting zone farther landward. The thermal structure of the wedge itself depends on convergence rate slab age and the thickness and heat production of the overriding plate. Numerical models of subduction zones that couple fluid release mantle flow and heat transfer predict narrow but persistent regions of high melt fraction above parts of the slab that intersect certain isotherms. These predictions are broadly consistent with seismological observations of low-velocity zones beneath volcanic arcs, and with magnetotelluric images showing regions of enhanced electrical conductivity beneath the arc front. The behavior of fluids in the slab also depends on whether they remain aqueous or become supercritical mixtures, and on how they interact chemically with rocks they traverse. Fluids that move through the slab and lower wedge can react with peridotite to form metasomatic assemblages, including new hydrous minerals such as amphiboly and phlogopite. These reactions store some of the incoming volatiles in solid form and change the composition of the mantle wedge. Subsequent heating or further fluid influx can destabilize these metasomatic minerals and release water again, generating new pulses of flux, melting at different stages in the evolution of the wedge. This sequence of hydration storage and renewed dehydration can produce complex spatial and temporal patterns of melt generation. Carbonates in subducted sediments and in altered oceanic crust introduce carbon dioxide into the system, which can either be released as a separate phase or participate in the generation of carbonated melts at particular depths and conditions. Such melts can have distinct compositions and melting behaviors compared with purely hydrous systems, further diversifying the magmatic products that may rise from flux-melted mantle. The overall efficiency of flux melting depends on how much fluid is delivered from the slab, on the time it spends in the reactive region of the wedge, and on the residence time of mantle material in that region. If fluid flux is high, and wedge flow continually brings fresh fertile peridotite into the zone of fluid influence, significant melt volumes can be generated. If fluid pathways are limited, or if wedge temperatures are relatively low, melting may be restricted, and fluids may continue upward with less interaction, perhaps contributing more directly to volatile contents at shallower levels. Observations of volcanic output along arcs show that magma production rates and compositions can vary markedly along strike, and these variations are commonly linked to along strike changes in slab structure, in sediment thickness on the subducting plate, and in convergence obliquity. In all cases, the defining feature of flux melting at subduction zones is that the primary trigger for melting is the addition of volatiles to hot mantle, rather than a large increase in temperature or a large reduction in pressure alone, and the resulting hydrous magmas carry signatures of both their mantle source and the recycled oceanic and sedimentary materials that supply the flux. Mantle plumes and deep mantle upwellings are proposed features of the convecting mantle that may provide additional pathways for generating magma, particularly beneath some hotspot volcanoes and large igneous provinces. In general, mantle convection regions of cooler, denser materials sink, often associated with subducting slabs, while regions of relatively warmer, less dense material rise. Most upwelling is broad and linked to plate separation at mid-ocean ridges or to return flow above subducting plates. Mantle plumes are instead described as more focused column-like upwellings, in which mantle with slightly higher temperature than its surroundings ascends from depth toward the base of the lithosphere. In many models, plumes originate near major thermal or compositional boundaries in the deep mantle, such as the boundary between the core and the mantle, where strong temperature contrasts and viscosity changes can favor the growth of buoyant instabilities. Laboratory experiments on fluids heated from below and numerical simulations of convection in planetary mantles show that such boundary layers can become unstable and form rising plumes when the contrast in density and temperature reaches certain thresholds. Although the mantle is solid on geological timescales, it behaves as a very viscous fluid, so the same physical principles can apply. A rising instability in such models often develops a leading region with a larger diameter followed by a narrower conduit that can continue to rise over long periods. Estimated temperature contrasts between plume material and the surrounding mantle are on the order of several tens to a few hundred degrees Celsius, which is enough to lower the density of the plume material and to influence melting behavior when it reaches shallower depths. As a plume upwelling moves into the upper mantle, it encounters lower pressures while retaining its temperature anomaly relative to the ambient mantle. Under these conditions, the adiabat for the rising plume material may intersect its solidus at greater depth than surrounding mantle that lacks the same temperature excess. This means that partial melting can begin deeper and over a thicker vertical interval compared with ordinary decompression melting beneath ridges. The volume of melt produced by a plume-related melting zone can therefore be significantly larger than that generated by typical passive upwelling alone. When such an upwelling reaches the base of the lithosphere beneath a plate, it can spread laterally, and the associated melting can give rise to extensive regions of basaltic magmatism. Large igneous provinces, which are regions where unusually thick sequences of basaltic rocks accumulate over geologically short intervals of time, are often interpreted as surface expressions of such plume upwellings reaching shallow levels. These provinces include continental flood basalt plateaus and oceanic plateaus. Their eruptive products are predominantly basaltic flows that stack to thicknesses of several kilometers, and geochronological data frequently indicate that much of this activity occurs within time spans of a few million years or less. The concentrations of magmatism in both space and time are consistent with a transient but high-volume melt source interacting with the lithosphere. After the initial phase associated with a large upwelling continued ascent in a narrower plume, conduit can maintain a more localized but longer-lived magma supply beneath a moving plate. As the plate moves across the region of focused upwelling, new volcanic centers can be constructed, while older ones move away from the main melting region and become inactive. This sequence produces age progressions along volcanic chains that can be matched with independently estimated plate motions. Some of the best documented hotspot tracks display such systematic age trends and align with present-day geodetic plate motion vectors, supporting a model in which the primary melt source remains approximately fixed in a deep mantle reference frame while the lithosphere moves overhead. Seismic tomography offers one of the main tools for investigating whether plume-like low-velocity structures exist in the mantle. Tomographic models, which are built from the travel times of seismic waves recorded at many stations, reveal regions where seismic waves travel slower than average, indicating zones that may be warmer, compositionally distinct or partially molten. Beneath certain hotspot regions, such as those under some major ocean island chains, tomographic images show columns or plume-shaped anomalies that extend from near the base of the lithosphere downward through much of the mantle, and in some cases appear to connect to broader low-velocity regions near the core mantle boundary. These images are consistent with the presence of thermally or compositionally buoyant upwellings. However, resolution decreases with depth, and laterally and different tomographic models do not always agree on the detailed geometry of these anomalies, so interpretations remain an active area of research. In addition to plume-scale structures, global tomography reveals two very large low-shear velocity provinces in the lowermost mantle beneath parts of Africa and the Pacific region. These broad features may represent regions of distinct composition or temperature that influence where more focused upwellings can form and rise, and some models propose that individual plumes originate from the edges or interiors of these provinces. The dynamic effects of plumes and deep upwellings can also be inferred from observations of surface elevation and gravity. Buoyant upwelling beneath a region can support long wavelength topographic swells in which land or seafloor stands higher than average over distances of hundreds to thousands of kilometers. Some hotspot regions are situated on such swells, and their gravity anomalies and uplift histories suggest that they are supported in part by dynamic pressure from rising mantle flow, rather than solely by crustal thickening or lithospheric density variations. Modelling of mantle flow constrained by tomography and plate motions can reproduce aspects of these swells, linking deep structures to surface observations. Geochemical data from hotspot-related volcanic rocks provide further clues about the origin and depth of their mantle sources. Isotopic ratios of elements such as helium, neodymium, lead and strontium in some ocean island basalts differ from those in mid-ocean ridge basalts. For example, certain hotspots exhibit relatively high proportions of helium-3 compared with helium-4, which is sometimes interpreted as a signature of mantle material that has been less processed by previous melting events and may reside in deeper mantle reservoirs. Other isotopic patterns point to contributions from recycled oceanic crust or sediments that have been subducted and stored at depth before being reincorporated into upwelling mantle. These geochemical fingerprints suggest that some plume sources may tap mantle domains with long and complex histories, some of which may be located near the base of the mantle or at other compositional boundaries. At the same time, not all intraplate volcanic regions show the same geochemical signatures, and some display compositions that can be explained by melting of upper mantle sources modified by prior tectonic events. This diversity indicates that deep focused upwellings are not the only possible origin for intraplate magmatism. The plume hypothesis is therefore one part of a broader framework for mantle dynamics, rather than a universal explanation. In some regions, shallow processes such as small-scale convection at the base of the lithosphere edge, driven convection near strong lateral contrasts in lithospheric thickness, or decompression, melting above zones of intraplate extension, may be sufficient to generate melt without invoking deep-rooted plumes. Distinguishing between these possibilities requires integrating evidence from seismic imaging gravity, surface uplift heat flow, and the spatial and temporal patterns of volcanism. Numerical models that couple plate motions, mantle rheology, and temperature-dependent viscosity show that both broad-scale circulation and more focused upwellings can arise spontaneously in a convecting mantle, and that their interactions with plates can produce complex patterns of melting and surface deformation. Deep mantle upwellings, whether in the form of narrow plumes or broader rising regions, are thus considered as integral components of whole mantle convection, and interact with subducting slabs and plate motions to shape where and how large volumes of mantle material approach depths at which partial melting becomes possible. Once partial melting has taken place in the mantle, the resulting magma occupies a network of pores and grain boundaries within the solid rock, and begins a journey toward shallower levels, moving through the lithosphere along pathways controlled by buoyancy pressure gradients, rock strength, and the existing pattern of fractures and heterogeneities in the crust. In most cases, mantle-derived magmas are less dense than the surrounding mantle, and lower crustal rocks, so there is a net upward buoyant force that tends to drive ascent. At the same time, the crust and lithosphere behave as elastic to brittle materials over many relevant timescales, and they are already structured by faults joints and layering. Magma must either exploit these structures or create new fractures as it rises, and it does so in ways that depend on its pressure relative to the surrounding rock, its viscosity, and the regional stress field. Near the base of the lithosphere and in the lower crust, melt extraction from the partially molten mantle may first occur by porous flow through interconnected pore spaces, but as melt fractions increase and the melt begins to form, channels flow often localizes into narrow conduits. Where the pressure of magma in these channels exceeds the normal stress across planes of weakness, or where it exceeds the tensile strength of the rock, new fractures can open. If the internal pressure of magma within such a fracture is sufficient to keep it open against the weight and stress of overlying rock, the fracture can propagate upward as a dike, which is a sheet-like body of magma that cuts across pre-existing structures. The orientation of a dike is controlled by the state of stress it tends to align, such that it is perpendicular to the least compressive principal stress, because this orientation minimizes the work needed to open a fracture. In extensional environments, dikes commonly strike parallel to the direction of rifting and dip steeply, whereas in other stress regimes their geometry can be more complex. Field studies of exposed dike swarms in eroded regions provide direct evidence for these processes, showing sets of roughly parallel dikes that can extend for kilometers in length and hundreds of meters in height, frozen records of former magma pathways that once fed eruptions or intruded into the crust without reaching the surface. As magma-filled fractures propagate, they respond to both the internal dynamics of the flowing magma and the mechanical properties of the host rocks. The front of a propagating dike experiences a concentration of stress at its tip, and small variations in rock toughness layering or pre-existing discontinuities can cause deflections, branching, or arrest. Where the dike encounters a layer with markedly different mechanical properties, such as a strong contrast in stiffness or a pre-existing bedding plane, it may change trajectory. In some cases, magma that was rising in a steeply dipping fracture is redirected to spread laterally along a mechanically favourable horizon, forming a sill. Sills are sheet-like intrusions that are approximately parallel to stratification or to compositional boundaries in the crust. Networks of dikes and sills can develop with vertical feeders connecting to horizontal intrusions, creating a three-dimensional plumbing system through which magma can migrate and temporarily reside. In regions where magma supply is sustained, repeated intrusion along similar pathways can build dike swarms several kilometers wide and many kilometers long, increasing the permeability of the crust to later magma batches. The rate at which magma ascends through dikes and conduits depends on several factors. Buoyancy provides a driving pressure that increases with the vertical distance between the source region and the current position of the magma, but this driving force must overcome viscous resistance to flow within the conduit and the stress required to propagate the fracture. Low viscosity magmas with relatively low crystal contents can move more rapidly than more viscous crystal-rich magmas under similar conditions. The width of the fracture also influences ascent rates with wider dikes, allowing faster flow for a given pressure gradient. Heat loss to the surrounding rocks occurs during ascent, especially if the magma rises slowly or pauses, and this cooling can increase viscosity and cause crystals to grow, which may slow or stop movement. In some circumstances, magma can solidify in place, freezing the conduit and preserving a dike or sill as a solid intrusion. In other cases, only the margins of the conduit cool sufficiently to form a solid carapace, while the interior remains molten for longer, allowing continued flow. Seismic and geodetic observations at active volcanic regions often record signals that can be interpreted as dike intrusion events. Swarms of earthquakes with similar focal mechanisms and migrating hypercenters can trace the propagation of a dike over distances of several kilometers in a matter of hours to days. Surface deformation patterns measured by ground-based instruments or satellite radar interferometry can show characteristic displacements consistent with the opening of a sheet, like intrusion at depth. These observations indicate that magma-filled fractures are dynamic structures that can transport significant volumes of melt through the crust on relatively short timescales, compared with the longer intervals between major eruptions. At the same time, not all magma that begins to ascend reaches shallow depths in a single uninterrupted episode. Magma can stall at levels where its density becomes similar to that of the surrounding rocks, where changes in the stress field reduce driving pressures, or where the rheology of the host rocks favours lateral spreading rather than further ascent. Such levels are sometimes referred to as neutral buoyancy zones. At these depths, magma may begin to pond, forming lens-shaped bodies, or irregular accumulations that can evolve into magma reservoirs or plutons if they remain molten or partially molten for extended periods. The development of these reservoirs is linked to the interplay between magma supply rate, heat transfer, and the mechanical response of the host rocks. Multiple pulses of magma can accumulate in the same general region, and their interactions contribute to the growth and modification of crustal magma bodies. Crustal heterogeneity exerts an additional control on magma pathways. Differences in composition, temperature, and fabric within the crust create zones of varying strength and permeability. Fault zones, shear zones, and older intrusive contacts can act as preferential channels if they are favourably oriented relative to the stress field, while strong intact blocks may deflect or impede rising magma. The presence of partial melt or high fluid pressures in certain layers can further lower effective strength and facilitate intrusion. Magma that passes through these heterogeneous regions can also interact chemically with the surrounding rocks, leading to partial melting of the host assimilation, or to reactions that alter both magma and wall rock. These interactions are strongly dependent on temperature composition and residence time, and are more fully expressed where magma stalls or moves slowly. Regions that now deeply eroded expose the remnants of ancient magma pathways. In some deeply uplifted terrains, geologists observe vertically oriented dike swarms cutting through crystalline basement horizontal sills interleaved with sedimentary sequences and larger intrusive complexes that represent the frozen cores of former magma transport systems. These exhumed structures provide constraints on the scales and geometries of magma pathways and on the volumes of magma that can be transported through the crust outside of eruptive episodes. Their orientations and cross-cutting relationships record the stress fields that governed magma emplacement at the time of intrusion. Geophysical imaging complements these field observations in less accessible regions. Seismic tomography can reveal low-velocity zones that indicate regions where high temperatures partial melt, or both are present, while receiver function studies can detect sharp contrasts associated with large sills or layered intrusions. Magnetotelluric surveys identify zones of high electrical conductivity consistent with interconnected melt or fluid networks. When these methods are applied around active or recently active volcanoes, they frequently identify complex multi-level networks of low-velocity and high-conductivity features that extend from the lower crust to shallow depths, consistent with a branching magma plumbing system. Across different tectonic settings, the combination of buoyancy, stress, mechanical layering, and pre-existing structures leads to a wide variety of magma pathways. But in all cases, the ascent from mantle source regions to shallower levels requires magma to move through the lithosphere in fractures and conduits whose geometry and evolution are controlled by both the physical properties of the magma and the solid earth materials it traverses. Magma storage zones within the crust form where ascending melts collect slow down or temporarily stall, and these regions play a central role in determining how magmas evolve physically and chemically before any eruption occurs. In many volcanic systems, geophysical and petrological evidence indicates that magma does not reside in a single large cavity filled uniformly with liquid, but rather occupies complex networks of melt-rich regions embedded within partially crystalline and partially solid rock. The term magma chamber is often used in a broad sense to refer to these storage regions, which can vary in size from small lenses a few hundred meters across to larger bodies extending over tens of kilometers. Their shapes are controlled by the mechanical structure of the crust, the distribution of fractures and faults, the stress field, and the history of previous intrusions. At depth, pressures and temperatures are high enough that injected melts can remain molten or partially molten for extended periods, while heat transfer to the surrounding rocks and ongoing crystallization gradually change the physical properties of the stored magma. The density of magma in a chamber depends on its composition, temperature, and crystal content. Newly arrived mantle-derived melts are typically hot and relatively low in silica, with lower viscosity and lower density compared with cooler, more evolved magmas that have crystallized some of their early forming minerals. As crystallization proceeds, solid crystals with specific compositions separate from the liquid. In many systems, early crystals include minerals rich in magnesium and iron, and their removal from the melt leaves the remaining liquid enriched in silica and in certain incompatible elements. This process, known as fractional crystallization, can generate compositional gradients within a chamber and can produce a spectrum of magmas from an initially basaltic input. The rate at which crystals form and segregate is influenced by cooling rate, degree of undercooling, and the presence of convection within the melt. Thermal and compositional convection can stir the chamber, transporting heat and crystals, and either enhance or partially offset chemical stratification, depending on the balance between buoyancy forces and viscosity. Volatile components, especially water, carbon dioxide, and sulfur-bearing species, are dissolved in magma at depth under high pressure. The solubility of these volatiles increases with pressure and decreases with decreasing pressure. As magma ascends into shallower parts of the crust, or as pressure is reduced through unloading, volatile components may become supersaturated. At this point, a separate vapor phase begins to form initially as small bubbles that nucleate on mineral surfaces or in the melt itself. The growth and coalescence of bubbles change the physical properties of the magma. An increasing gas fraction lowers the bulk density of the mixture, but can increase its effective viscosity if bubbles are abundant and deforming slowly. The distribution of bubbles can become stratified if gas-rich lower density layers accumulate near the top of a chamber, while denser crystal-rich magma settles toward the base. This vertical arrangement of layers with different densities, viscosities, and compositions contributes to the internal architecture of magma storage zones. In many systems, repeated injections of fresh magma from deeper sources recharge existing reservoirs. These recharge events introduce new heat mass and volatiles into the system. If incoming magma has a different composition temperature or volatile content than the resident magma, mixing and mingling processes occur. Complete mixing can homogenize the chamber, while incomplete mixing may preserve bands, enclaves, or other structures representing contrasting magmas that have interacted without fully blending. The intrusion of hotter, less viscous magma into cooler, more crystalline material can remobilize previously accumulated mush zones, which are regions where solid crystals are suspended in interstitial melt. Such mush zones may form the outer parts of a storage complex, grading inward to regions with higher melt fraction. The boundaries between melt-rich and melt-poor domains can migrate as heating or cooling progresses, and as melt is added or removed. The mechanical behavior of the host crust around a magma chamber responds to changes in pressure and volume within the storage region. As magma accumulates, the total volume of the chamber may increase, exerting pressure on the surrounding rocks. This internal overpressure can cause elastic deformation, and if stresses exceed the strength of the rocks, the formation or reactivation of fractures. Conversely, solidification and withdrawal of magma can reduce internal pressure, allowing the chamber roof to subside or fracture in different patterns. The magnitude and distribution of these pressure changes depend on the geometry of the reservoir, its depth, and the properties of the encasing rocks. Geodetic measurements around active volcanoes frequently detect surface deformation patterns that are consistent with pressure variations in subsurface magma storage regions. Uplift or subsidence patterns combined with seismic data that locate swarms of small earthquakes around reservoir margins indicate that magma chambers and associated mush zones are mechanically coupled to their surroundings. Overpressurization of a magma storage system is one of several conditions that can precede an eruption. Overpressure can result from the addition of new magma, from increased volatile exsolution, as pressure drops or as crystallization proceeds, or from external tectonic stresses that change the loading on the chamber. If internal pressures grow sufficiently high, fractures may propagate upward from the chamber roof, or laterally into surrounding rock, providing new pathways for magma to leave the reservoir. Whether such fractures reach the surface or link to pre-existing conduits depends on the stress field, on the presence of structural weaknesses, and on the density contrast between magma and wall rock. In some cases, intrusions remain confined within the crust, forming sills and dikes that redistribute magma without leading to surface eruption. In others, fractures connect to shallow levels and ultimately to vents where eruptions occur. The readiness of a magma body to erupt is not determined by pressure alone. The rheology of the magma, including its viscosity, crystal content, and bubble content, influences how easily it can flow once a pathway is available. High viscosity, crystal-rich magmas may require higher pressures to push through narrow conduits, and may favor explosive fragmentation if gas cannot escape efficiently. Low viscosity, crystal-poor magmas can move more readily and may favor effusive eruptions under similar pressure conditions. The existence of compositional or rheological layering within a chamber means that different parts of the reservoir may respond differently to the same stress changes. A rupture that taps the uppermost gas-rich portion of a chamber can lead to a different style of eruption than one that intersects deeper, less evolved magma. Petrological studies of erupted rocks, including phenocryst assemblages, mineral zoning, and melt inclusions, provide information about the storage conditions and pre-eruptive evolution of magmas. Mineral compositions record the temperatures, pressures, and volatile contents at which they grew, while zoning patterns indicate changes in these conditions over time. Melt inclusions trapped within crystals preserve samples of magma at earlier stages, sometimes retaining volatile contents that reflect deeper storage levels before degassing at shallow depth. When these observations are combined with geophysical data that map the size and distribution of low-velocity zones beneath volcanoes, a picture emerges of magma reservoirs as dynamically evolving regions where injection crystallization, volatile exsolution, and mechanical deformation proceed together. Not all volcanic systems possess large, long-lived chambers. In some, magma may reside mainly in smaller transient accumulations, or in networks of dikes and sills that coalesce only briefly before eruption. In other systems, substantial batholith-scale intrusions in the deep crust represent the intrusive counterparts of magma that did not erupt but instead cooled slowly, contributing to long-term growth of continental crust. Across this range of settings, the structure and evolution of magma storage zones exert a strong influence on the timing, magnitude, and style of volcanic eruptions by regulating how mantle and lower crustal melts are modified, where they reside, and under what conditions they can leave the crustal reservoir to feed surface activity. Volcanic edifices and vents at the surface are the visible products of many eruptions acting over time, and their shapes, sizes, and internal structures reflect the properties of the magmas that build them, the ways in which eruptions occur and the rates at which they are modified by gravitational instability and erosion. A volcanic edifice can be defined as a topographic construction made primarily of volcanic rocks that accumulate around one or more vents. Vents are openings through which magma gases and fragmented material reach the surface, and they can take the form of circular craters, elongate fissures, or more complex fracture networks. In some systems, a central vent dominates and feeds most eruptions, while in others, numerous vents are scattered across a volcanic field. The growth of an edifice usually involves repeated episodes in which magma rises through conduits, erupts at or near vents, and deposits lava and fragmented material that stack into a three-dimensional body. Between eruptive episodes, compaction, cooling, intrusion of new magma, and surface processes continue to modify the structure and shape of the volcano. The style of eruption and the resulting landform depend strongly on magma viscosity, gas content, and temperature. Low-viscosity magmas, which are typically hotter and poorer in silica, can flow readily and form thin to moderately thick lava flows that travel significant distances from their source. When such magmas erupt repeatedly from a central region, they can build broad, gently sloping shield volcanoes. Individual lava flows spread out in overlapping layers, and the edifice thickens over time as flows are emplaced one above another. Shield volcanoes often have low average slopes, reflecting the ability of fluid lava to travel far before solidifying. Their internal structure consists mainly of stacked flow units, with intercalated breccias and intrusions cut by radial dikes that represent former pathways for magma. Some shields are also characterized by rift zones, which are linear belts of fissures and intrusions that extend away from the summit region and concentrate flank eruptions. In contrast, higher viscosity magmas richer in silica and often cooler at the time of eruption do not flow as easily. When these magmas contain substantial dissolved gases, decompression during ascent can cause rapid bubble growth and fragmentation, leading to explosive eruptions that produce pyroclastic material such as ash lapilli and blocks. Repeated alternation of lava flows and pyroclastic deposits around a vent builds steep-sided stratovolcanoes, also called composite volcanoes. Their slopes are steeper than those of shield volcanoes because many of the deposits are relatively weak angle of repose, limited beds of loose or only weakly welded fragments, interlayered with shorter lava flows that buttress the flanks. The internal stratigraphy of a composite edifice can be complex with channelized pyroclastic density. Current deposits fall layers and lava units interfingering. Intrusions such as dikes and sills cut this layered pile, feeding eruptions or remain entrapped as solidified bodies that strengthen or locally weaken the edifice, depending on their geometry and the degree of alteration. Lava domes form when very viscous magma with high silica content extrudes slowly at the surface. Instead of producing far-reaching flows, the magma piles up over the vent as a thick, stubby mass. Growth occurs by the extrusion of new magma at the core or base of the dome, and by brittle failure and gravitational spreading at the margins. The outer parts of domes often become fractured and produce rockfalls and block and ash flows that accumulate around the dome, forming aprons of breccia. Domes can grow within craters of larger volcanoes or on their flanks, and they can cap conduits as a solidified plug that influences subsequent pressure buildup. The stability of a dome depends on internal strength slope and the rate at which magma is supplied. Failure can be triggered by internal pressurization, by seismic shaking, or by removal of support at the base. Small steep-sided scoria cones, also known as cinder cones, are constructed mainly from fragments of basaltic to intermediate composition magma that has been fragmented by gas expansion during relatively short-lived eruptions. During such eruptions, fountains of molten fragments fall back around the vent and accumulate as beds of scoria and spatter that dip away from the crater. The resulting cone typically has slopes near the angle of repose for loose fragments. Many scoria cones are monogenetic, meaning that they are built during a single eruptive episode or closely spaced set of episodes and do not erupt again. They are commonly associated with small lava flows that breach the cone or emanate from its base, and they often form in fields where many cones are scattered across a broader volcanic province. These fields record the distribution of small, relatively short-lived magma batches along fractures in the upper crust. Another class of surface landforms includes volcanic plateaus and flood basalt provinces, which are constructed not by a single central cone, but by extensive laterally continuous lava flows that issue from fissure systems. Individual flows in such provinces can cover large areas and reach thicknesses of many meters, and their accumulation builds gently undulating plateaus rather than solitary high peaks. The internal architecture of these plateaus consists of stacked flow units, with baked zones and sedimentary interbeds that represent pauses between eruptive episodes. Caldera structures are large depressions that form when the roof of a shallow magma reservoir collapses following substantial withdrawal of magma, often during or after a large explosive eruption or a series of eruptions. A caldera is generally larger than a typical crater and may have a complex ring fault system at its margins. During caldera formation, subsidence can be accommodated by inward dipping faults that cause blocks of the roof to drop. The resulting depression can later host new volcanic activity, including the growth of post-caldera domes and cones, and can be infilled by sediments and lava flows. The internal structure of caldera-related systems includes thick ignimbrite sheets from pyroclastic density currents, as well as intrusive ring complexes where dikes and sills follow the caldera margin faults. Over longer timescales, constructional processes on volcanic edifices are countered by various forms of degradation. Gravitational instability can cause landslides and sector collapses, where large portions of a volcano flank fail and move downslope, leaving amphitheatre-shaped scars and depositing debris avalanches on surrounding lowlands or seafloor. Hydrothermal alteration driven by circulation of hot fluids through the edifice can weaken rock by converting strong minerals into clays and other weak phases, thereby promoting failure. Erosion by rainfall, rivers, glaciers, and coastal processes progressively removes material from the volcano surface, incisors valleys, and exposes internal structures such as dikes, conduits, and layered deposits. The balance between construction and erosion depends on eruption frequency, tectonic uplift, or subsidence and climate. In high-standing composite volcanoes and domes, erosion can reveal complex internal stratigraphy and intrusive networks while the external cone is still present, whereas old inactive volcanoes in regions of strong erosion may be reduced to deeply dissected remnants where only parts of the original edifice are preserved. Vent distributions on volcanoes and within volcanic fields reflect the arrangement of underlying conduits and the regional stress regime. Central vents often overlie long-lived conduits that connect to crustal magma storage zones. Flank vents and fissures commonly align along structural trends such as rift zones on shields or fault lines on stratovolcanoes, indicating where stress and pre-existing structures favour dike propagation. In monogenetic fields, vents may cluster along linear or arcuate belts that mark zones of crustal weakness or changes in stress orientation. Mapping of vents combined with structural analysis allows reconstruction of the orientation of principal stresses acting during eruptions and helps to constrain the growth history of the volcanic system. Over geological timescales, repeated eruptions, intrusion, gravitational adjustment and erosion together produce a spectrum of volcanic landforms whose dimensions and internal structure depend on magma properties, eruption style, and the tectonic and climatic context in which they evolve. Lava ash and volcanic gases that leave a vent eventually become solid rocks, or deposits with internal structures on the scale of crystals, bubbles, and glass fragments, and these microscopic features preserve information about the conditions under which the magma formed, rose, and erupted. When lava erupts and flows across the surface, it cools from the outside inward. The rate of cooling, the viscosity of the magma, and its composition all influence the textures that develop as the melt crystallizes. Rapid cooling at or near the surface tends to produce fine-grained or glassy rocks, in which individual crystals are too small to be seen without magnification, whereas slower cooling at depth allows larger crystals to grow. Many volcanic rocks show porphyritic textures in which larger crystals are set in a finer-grained matrix. The larger crystals, often called phenocrysts, typically grow earlier in magma storage zones at higher temperatures, while the finer matrix forms from the remaining melt as it cools more quickly during ascent and after eruption. The mineral assemblage present in these crystals and their relative proportions reflect the composition of the magma and the pressure and temperature conditions during their growth. For example, mafic lavas commonly contain olivine and pyroxene phenocrysts, whereas more silica-rich lavas may contain feldspar and quartz. At the microscopic scale zoning within individual crystals records changes in the composition of the melt or in growth conditions over time. Concentric bands of slightly different chemical composition can form as the magma evolves by crystallization, or as batches of different magma mix. These zoning patterns can be imaged and analyzed to reconstruct the sequence of events experienced by the magma before eruption, such as episodes of recharge by new melt changes in temperature or variations in pressure and volatile content. In some cases, resorption textures where parts of a crystal appear corroded or rounded indicate periods when the crystal became unstable and partially dissolved back into the melt, possibly due to changes in temperature or composition during mixing. The glassy component of many volcanic rocks forms when melt cools so rapidly that it does not have time to crystallize. Glass can occur as continuous matrix between crystals in lavas, as individual clasts in pyroclastic deposits, or as thin rims on crystals and rock fragments. Under the microscope, volcanic glass appears as an isotropic material lacking internal crystal structure. In some rocks later, devitrification of glass leads to the formation of microcrystalline aggregates or spherulites, which are radial or fibrous clusters of new crystals. The presence and distribution of glass and the degree of devitrification depend on cooling history composition and subsequent thermal and chemical alteration. Vesicles are cavities in volcanic rocks formed by gas bubbles that exsolve from magma as pressure decreases during ascent and eruption. The size, shape, and distribution of vesicles provide constraints on bubble nucleation growth and coalescence. In basaltic lavas, vesicles can be spherical or elongated, sometimes aligned along flow directions, indicating deformation of bubbles in moving magma. High vesicle densities near the tops of flows compared with interiors reflect segregation of gas toward the upper parts of the lava as it degasses and cools. Variations in vesicle size distributions within a single rock can indicate multiple stages of bubble growth or episodes of gas loss and replenishment. In more viscous magmas, vesicles may become highly irregular and interconnected, forming networks that affect permeability and gas escape. The transition from closed vesicles to connected vesicle networks is important for eruption style, because efficient gas escape can limit explosive fragmentation, whereas gas trapped in a viscous melt can lead to high internal pressures. In pumice and scoria, which are highly vesicular ejecta produced by explosive eruptions, the rock consists of a framework of glass or crystal-supported walls separating bubble spaces. Pumice, typically associated with silica-rich magmas, has low density and high porosity due to a high proportion of vesicles with thin glass walls. Scoria, more common in mafic eruptions, also contains abundant vesicles, but their walls are thicker and the overall density is higher. Under magnification, the shapes of vesicles in pumice often show evidence of rapid bubble growth and deformation, including stretched and coalesced forms. These features indicate that gas exsolution bubble expansion and magma deformation occurred on short timescales as the magma decompressed. In pyroclastic deposits, ash particles derive from fragmented magma display, distinctive microscopic morphologies. Many ash grains are glass shards with sharp cuspate outlines that reflect brittle fragmentation of vesicle walls. Some shards show Y-shaped or convoluted terminations, where three or more vesicle walls met before breaking, while others have blocky shapes associated with more massive melt fragments. The proportions of shard types, crystals, and lithic fragments in an ash sample help identify whether fragmentation was driven mainly by magmatic gas expansion, by interaction with external water, or by mechanical breakup of pre-existing rocks. Welded tuffs formed when hot ash and pumice accumulate and compact under their own weight, while still above the glass transition temperature show microtextures, where originally separate pumice clasts are flattened and fused. These flattened pumice lenses, sometimes called fiamme, preserve elongated vesicle shapes, aligned with the direction of compaction. The degree of welding can be assessed by the extent of grain boundary fusion, vesicle deformation, and the presence of eutaxitic textures which record alignment of pumice fragments and shards. Such features inform on emplacement temperature depositional load and the thickness of the pyroclastic flow or fall deposit. Crystals in pyroclastic rocks include both phenocrysts that grew in the magma prior to fragmentation and smaller microlites that crystallize during rapid cooling of ash and pumice. Microlite textures are sensitive to cooling rate and undercooling. High microlite densities and aligned microlites can reflect rapid crystallization during decompression and prior to fragmentation, while sparsely microlitic glass indicates very fast quenching. flow banding observed at scales from hand sample to thin section consists of layers or streaks with differing proportions of crystals, vesicles, or glass, often reflecting variations in strain or in melt composition during flow. In lava domes and highly viscous flows, flow banding can be pronounced, and microscopic examination reveals alternation of crystal-rich and crystal-poor bands or bands with different vesicle densities. These features record shear localization and the interaction between deformation and crystallization in slowly moving viscous magma. Chemical analysis of individual crystals, glass and melt inclusions complements textural observations. Melt inclusions trapped within crystals during growth preserve samples of melt at earlier stages of evolution, including volatile contents that may no longer be present in the bulk rock after degassing at the surface. By measuring the concentration of water, carbon dioxide, sulfur, and other volatile species in melt inclusions at different depths of entrapment, it is possible to infer pressure conditions during storage and ascent, and to reconstruct degassing histories. Crystal chemistry and zoning patterns also provide evidence for episodes of magma mixing and for changes in oxidation state. Together with trace element concentrations and isotopic ratios in whole rocks, these microscale measurements form a record of sources, differentiation processes, and timescales of pre-eruptive evolution. Fragment-shaped surface textures and internal structures are also important in understanding how deposits are reworked after deposition. Abrasion of ash particles during transport in pyroclastic density currents can round edges and produce impact marks. Alteration by hydrothermal fluids can replace glass with secondary minerals such as clays, zeolites, or silica polymorphs, changing both the mechanical properties and the permeability of deposits. In settings where volcanic rocks are later involved in sedimentary processes, volcanic grains may appear as components of sandstones and conglomerates carrying volcanic textures into the sedimentary record. The cumulative effect of these microscale features is that solidified lava flows, pyroclastic layers, and reworked volcanic sediments each contain detailed physical and chemical structures that reflect specific combinations of magma, composition, temperature, volatile content, ascent rate, fragmentation, mechanism, cooling history, and post-depositional modification. By examining volcanic rocks under magnification and analyzing their mineral and glass chemistry, it is possible to relate observed textures to the processes of magma generation, ascent storage, and eruption that occur at larger scales within Earth's crust and mantle.